Here's an example of how to use LoggerPro in combination with a spreadsheet program to make a nice graph of some data, do a curve fit to it, and calculate a chi-squared. So here we can see some data that I have, just sample data with some errors thrown in, and we have the x and the y and the uncertainty. Okay, so the first thing that I want to do uh, with this data is calculate 1 over the uncertainty squared. And so I will do that 1 over this cell squared, and then I can copy down. So the reason for that is because I'll want the uncertainty column so that I can make the error bars, but um, the LoggerPro software doesn't do a chi-squared automatically, but we can weight each data point. And the weight in the definition of the chi-squared is 1 over the uncertainty squared. And so if we have this column, we can use that as the weight. Okay, so I will copy all 4 of these columns and go over to LoggerPro. So LoggerPro starts out with just this 2 columns, X and Y, and um, uh, probably the easiest way, I mean, I'm sure there's a way to add columns, but if I just copy these 4 in, I can see that it creates these 2 new columns. So before I forget what those are, I can um, double click on that column and go to column definition and change that to uncertainty and whatever I want to. I mean, I guess I could use delta for this. Um, let's, I know that this is just X and Y, but let's change it to something with units. So we'll say so we'll say rather than X, we'll call that time, which is short name T, and units of seconds. Right, and then for the Y, we can make that, I don't know, a distance, short name X, and units meters. Okay, and then just so that I remember what this other column is, I'll rename that. I'll call that 1 over uncertainty squared. Okay, and then you'll probably want to change the way that this displays a little bit. So I can, if you double click on one of these axes, I like to just do auto scale for these. And that'll give you something where all the points are fit in. Now you can see that these are right at the edge, which is maybe not great, so you might want to change the boundaries a little bit. But usually I find that auto scale larger. I mean, let me see if I do auto scale larger. Actually, it didn't change anything. Okay. Sometimes it just zooms out too much. You can see that changing the names of the columns changed what's displayed on these axes, which is nice. Okay, now I want to display the error bars, so what I can do is I can right click and go to column options and go to distance, that's my y-axis. And for options, I can select error bar calculations and use column. And then I can use the uncertainty as my error bars. And so now I can see those there. Okay. And depending, you might also want to change, like when I want to put this up on the projector, usually I'll change these to a filled circle and make them large. The only time that a filled circle would be bad is if the error bars are much smaller than this. It can be kind of hard to see them. Okay, so we have that. Okay, so that's a nice display of our data and the uncertainties. Now, when we do our fit, what we want to go to analyze, and even if you're doing a linear fit, you want to select curve fit because that gives more options like doing the weighting and things like that that you'll need. So you never want to just do the linear fit button. Okay, so you can choose any equation that you want. We're doing a linear fit here. We want automatic. We'll select create a calculated column, so that'll give us what the each data point is calculated by the model, which we'll be using to calculate the chi-squared. Show the curve fit, that just means that it's going to draw the best line. And then we want to use weight column to do 1 over the uncertainty squared. Okay, so anytime that you're this is doing a chi-squared best fit. It's going to minimize now, or it's going to take the error bars into account rather than just doing the ordinary least squares fit. All right, and we can try the fit to make sure that everything looks okay. Sometimes you might have accidentally selected something dumb like power law, or something that doesn't apply. And when you try the fit, you say, oh, I still had it set to the old settings. So linear. Okay, try the fit. It shows the values there. Make sure that we have curve, show curve fit, create calculated column, and weight by 1 over uncertainty squared. And okay. So there we get that box that comes up that shows us the value of the slope, which is given with units, which is good. It shows the uncertainty in the slope. It shows the intercept and the uncertainty in the intercept. And then these other goodness of fit statistics that we don't really use. We're more interested in the chi-squared. Okay, so you can do things like we talked about. Make sure kind of look visually here. Are there about the same number of data points that are above the line as below? Do we get about 2/3 of the error bars, or do we go through about 2/3 of the error bars, which is what we would expect? You can print this, and probably want to print as a PDF, or you can do some sort of screen grab to get this plot. But so this shows a pretty good fit, we think, and but a better test for that is to take this. Okay, so this column here is the data calculated column. So I can highlight that and copy it and bring it back to my spreadsheet. And so I can say that this is the fit. I guess I should say, be more specific and say it's the linear fit. And so then I can calculate, first of all, the variance, which is just the data point minus the fit. Or really, you could do vice versa, because unless you're going to do plot the residuals, you can the main thing is that we're going to find the variance squared, right? So we can make the next line, or the next column, the contribution to chi-squared, right? So for each data point, we want to take the variance squared and divide it by the uncertainty squared, and copy that down. And then the chi-squared is the sum of all those. So, oops, not chi-cubed, chi-squared. That's the sum of all those, so I can write sum from here to there. And then we also would like the reduced chi-squared. So that's going to be equal to the chi-squared divided by the number of degrees of freedom. Now, the number of degrees of freedom is the number of data points, so I could do a count, or you could just count by hand. Usually we don't have that many data points. And then subtract the number of parameters in the fit. So this is a linear fit. I've got slope and intercept. Those are my those are 2 parameters. So number of data points is 11 minus 2 parameters is going to give me 9 degrees of freedom. So then there's our reduced chi-squared, about 0.85. So we know that's less than 1, but not which is, but it's close to 1, which is what is expected. And you can use that in the lookup table to find um, the um, percentage chance, or the percentage of the time that you would expect the chi-squared that large if the model is correct. So there you go. We've got a fit that takes the error into account. The error bars are nicely shown on the plot. We have the slope with uncertainties. So that's a standard error in the slope and standard error in the intercept, which means 1 standard deviation. And then we've got our chi-squared and reduced chi-squared values.